Hi group, it's Mrs. Schaus, here to take a look at section 1.4 notes with you, where we are talking about finding the domain of rational expressions. This should probably say function here. We know that domain means the set of input values when we're talking about a function that is input and output. We want to be able to do some things with rational expressions. Simplify, perform operations, and deal with compound, or really what we call complex fractions when we're dealing with fractions within a fractions, and we call them complex if we're dealing with variables. I'll let you read the success criteria on your own, since you're going to have a copy of those notes in your possession. So what I really want to do is to begin by taking a look at a couple of reminders. What does it mean to have a rational expression? Well, a rational expression simply means that it's a fractional expression. And recall that, like I mentioned a moment ago, domain really means the set of permitted real numbers for the input variable. You know, the set of real numbers that define the function. Okay, in these first three examples, they ask us to actually find and then state the domain. I want to kind of try to generalize this for you. When we're dealing with these rational expressions, there are two concerns that we have about potential input values. One is whether or not they make a denominator equal to zero. We know that division by zero isn't defined, so we would want to restrict and say that x couldn't be any values that make the denominator equal to zero. The other thing is that if we have any radicals and those index, the index on the radical were an even number, that we can't take the root of a negative expression. So once again, we would want to restrict it so that what's underneath the radical would be non-negative. Okay, let's dig into these then. In this first problem, again, the concern is, are there values that make the denominator equal to zero? So I actually want to start by setting the denominator equal to zero and trying to find those values that will create the zero. Now, this one happens to factor pretty nicely here. That's a +4 and a -1. So using the zero product property, x plus 4 would be 0, or x minus 1 would be 0. So x equals -4, or x equals 1. Now, I don't want to circle these like these are solutions to something. What they're actually solutions to, again, are this equation that I created trying to find what values make the denominator equal to 0. So when it actually comes to stating my domain, I want to say that it's all x that are elements of the reals, but not equal to -4 and not equal to 1. So I know I found these values to be -4 and 1, but it's restricting and saying that the domain cannot include those elements. All right, I put b in here because I wanted to make sure that I clarified if your function is a polynomial, then that means that the domain will always be the entire set of reals. Let's move on to C. Now, I want you to think for just a minute. There are, sort of two things that should be running through your mind here. One is that business of the denominator equaling 0. Since I have just an x here, I need to be thinking to myself, x cannot equal 0. But beyond that, I also have to deal with this radical. So I want to say, hey, what's underneath the radical, namely x minus 3, has to be non-negative. It can be greater than or equal to 0. And if I solve that inequality by adding 3 to each side, I get x is greater than or equal to 3. So I need to put these two ideas together to write my domain. So I'm going to say the domain are all x's such that x is greater than or equal to 3. And I might be tempted to say, and x cannot equal 0 here. But if the x's are already required to be greater than or equal to 3, it would be redundant to say x not equal to 0. In some situations, let's go back and say this had said x is greater than or equal to -2. Well, 0 would fit in that category, so I would also have to have said over here not equal to 0. One other thing to keep in mind, if I had this root in the denominator, instead of saying what's underneath the radical could be greater than or equal to 0, I would have to say strictly greater than 0, because again, I couldn't have the equality of 0 if it were in the denominator. Okay, so that's a little bit about finding and stating domain. Let's take a look at simplifying and then performing some operations with these rational expressions. So first of all, in simplifying, I want to look at each numerator and denominator and see if they factor. This does factor pretty nicely here, x plus 5, x plus 3. A difference of 2 squares sits below, so x plus 5, x minus 5. And now that I have them factored, just like with any fraction, if there is a common factor in the numerator and in the denominator, those will simplify the expression. X plus 3 over x minus 5. Now you can leave this in parentheses if you want, or you can leave them out at this point. It's really up to you. But one thing I want you to make sure that you understand, over here I was canceling these groupings. That's because they are factors. I'm multiplying the factor or the whole quantity x plus 3 times, this is x plus 5 times x plus 3 here. Here, some folks, students who are maybe young in some of their understandings of mathematics will want to say, I can cancel this x with this x that sits down below. But because of this addition, this x is a term rather than a factor. So I can't reduce any further. Okay, let's take a look at some operations now. Here I'm doing some multiplication. And once again, like I had stated, I want to try to factor where I can. Let's see, x here and here. I've got one of each sign. 7 here, 4 here. That'll give me the negative 28 I'm looking for, but combined to give me 3x. Down below, I could leave just as x plus 1 squared, but maybe you just want to write it as x plus 1 times x plus 1 in case there's another x plus 1 factor. We'll see if there is. The numerator here for the second fraction. I'm going to need, again, one of each sign. A positive 1 and a negative 5 will do the trick for me. So there's one of those x plus 1s I was talking about. And let's factor the bottom here as well. Plus 6 and minus 4 will do the trick for me there. There we go. All right, so now once again, I'm looking for common factors in the numerator and denominator so that I can simplify the fraction a bit. I see the x plus 1 here and here as well. So what I'm left with in the numerator is the quantity x plus 7 times the quantity x minus 5, and down below the quantity x plus 1 times the quantity x plus 6. I'm okay with leaving it in that form for now, but I want you to understand that if you were on an assessment, they may expand this out. And I fully believe that at this level, you guys are capable of doing that multiplication and giving me your answer in an expanded form. Okay, in the next one, we're looking at a division problem. You guys know the rule of dealing with division when we've got fractions. That is, you keep the first fraction, you switch to multiplication, and you take the reciprocal of the second fraction. So I'm going to put this x plus 3 up top and the x squared minus 1 down below here. Although I'd like to factor it, and it is a nice difference of 2 squares, there it is. The first fraction remains the same, but I'm going to write it in factored form. So x plus 3, x minus 1, and again down below, x plus 2, x minus 2, because I have a difference of 2 squares. I'm going to put this x plus 3 in a grouping. I can't cancel terms. I can only cancel it if it's the entire quantity. I don't see an x plus 3 down below, so let's see, what do I have? X minus 1 here, x minus 1 here. So my final answer is x plus 3 times x plus 3, and down below here, x plus 2, x minus 2 times x plus 1. Final answer could be left in this factored form or could be expanded. Now we've taken a look at multiplication and division, but now I want us to take a look at some addition. Just like with typical fractions, when we add or subtract, we have to have a common denominator. My common denominator here for this problem is going to need a factor of x plus 2 and a factor of x minus 3. That means that in order to get that common denominator, I've got to multiply essentially by a fancy form of 1. For this fraction, it's going to be x minus 3 over x minus 3. And for the second fraction, it's going to be x plus 2 over x plus 2. So I haven't changed the value of anything. I'm just multiplying by forms of 1 that give me that common denominator. Since I have a common denominator, I can now add up the numerators. And keep my common denominator. And now at this point, I just need to do some simplification. I'm going to distribute through the 5 and the 2x. And I'll just go ahead and multiply what I have down below as well. And I'll write my final answer here by combining like terms. So I would have 2x squared, got a 4x and a 5x, so plus 9x minus 15. And down below here, x squared. When I combine these 2x and the negative 3x, I get negative x minus 6. And we'll leave it in that cleaned up, expanded form. All right, let's take a look at a couple that are simplifying when we have a denominator that needs to be rationalized. We have already been working with rationalizing denominators where we were dealing with roots of different indices, but we didn't deal with rationalizing when there were more than one term in a denominator. So when I've got two terms like this, I want to multiply by a fancy form of 1, but it's going to look a little different than what we've been doing. I'm going to multiply by what we call the conjugate, which means I look at this denominator with its two terms and I rewrite both of the terms with the opposite sign in the middle. And I'm still multiplying by a form of 1, so it is 3 minus the square root of 7 over 3 minus the square root of 7. And we'll multiply across the top. The 2 gets distributed through, and I have 6 minus 2 square roots of 7. Now, this picking of opposite signs was very intentional. Watch what happens when we do the multiplication now. 3 times the 3 will give me 9. I get minus 3 square roots of 7. But now here, plus 3 square roots of 7. And finally, minus a square root of 49, or minus 7. Notice how it's very intentional that these two have opposite signs so that they will cancel one another, and I end up with a denominator that has no radical in it at this point. So 6 minus 2 square roots of 7 all over 9 minus 7, or 2. I can take it one step further because both of the two terms here contain a common factor of 2. So I'll factor that out. And again, simplify. And I'm left with 3 minus the square root of 7. Okay, one more like that to rationalize. Still have my two terms here. They have subtraction between them to start, so I'm going to use addition. Make it a form of 1. When I multiply on the top, I'm just distributing that 5. And down below here, a square root of x times another square root of x. That's the square root of x squared, so just x, plus the square root of x. Now minus the square root of x, and minus 1. Once again, these are opposites, so they cancel each other. And I'm left with 5 square roots of x plus 5 over x minus 1. No radical remaining in that denominator. Okay, I've got a couple of problems that are dealing with those complex, or maybe you've heard them called compound fractions. When we have a fraction within a fraction, we call it compound. When we use variables, we typically call it complex. Okay. what I want you to think is that in order to put more than one fraction together, we need a common denominator. Since there are two fractions just within this numerator, we need to be able to, again, put these together, and our common denominator for that top piece will be xy. If I change 2 over x to have a denominator of xy, I multiply by y in the bottom, so I multiply by y in the top. And similarly, to change the 1 over y to have a denominator of xy, I multiplied the bottom by x, so I do the same thing up top. Notice that I've kind of drawn this fraction bar a little bit more boldly than the others because I want us to recognize here's a fraction within another fraction. Here's my denominator of that whole thing. But this bar we really need to think of as division. All right, let me put these two together since they now have a common denominator. That's 2y plus x over xy, and then that is over xy over 12. The denominator in this problem already only contained one fraction. So at this point where I've got one fraction on top and one fraction on the bottom, I want to keep my top fraction, and the rule with dividing fractions, change to multiplication by taking the reciprocal of the second fraction. And so now at this point, I'm just going to multiply the 12 through and keep my xy squared, and xy times another xy. I could have written x squared y squared, or just the grouping squared would be fine. Okay. One more complex fraction to take a look at. I'm using 1 minus 6 over m plus 1 as the numerator. I can write that 1 as a fancy form of 1 with the denominator that matches the other. So m plus 1 over m plus 1 minus 6 over m plus 1. And likewise down below where I've got this fancy form of 1 again that I need to write, m plus 1 over m plus 1 plus 2 over m plus 1. I'm going to come down here for space sake. I'm going to combine the top here. M plus 1 minus 6 is really m minus 5 over m plus 1. And then there's my division bar. If I combine the numerators here, m plus 1 plus 2 more, that's m plus 3 over m plus 1. I've got one fraction on the top, one fraction on the bottom. And so now I could go ahead and keep the top fraction, change the division to multiplication by taking the reciprocal of the second. I notice that there's a factor in the numerator here that cancels with 1 down below. And I'm left then with m minus 5 over m plus 3. Okay, the last thing that we're going to look at together today is an application. And we do have an upcoming section that we typically cover where we do a lot of applications. And this is a bit of a lead into that. Now, this year, because of our current situation, some of this is going to be kind of tailored down, and we'll find places that we can to sort of fit some of the applications in. But I thought this would be a good time for us to at least take a look at how the equation was set up, even though we didn't have to really write it. This is still really just about us simplifying this rational expression. Let's take a look. A train travels 5 miles from town A to town B and then back again. The train travels 1.2 times as fast on the return trip. Let R equal the train's speed on the trip to town B. The equation below represents the total time of the round trip. Simplify the expression on the right-hand side. So even though we don't really have to make sense of the problem to be able to simplify, let's take a moment to see if we can. I think that all of you are familiar with the formula distance equals rate times time. Here, this expression is representing time, the total time that it took to take the trip out there and the trip back. So if I take that formula and I divide by R on each side, it really becomes distance divided by rate equals time. Well, in this scenario, there are two pieces of the trip: the time that it takes to travel from town A to town B, plus the time it takes to travel back. How far was the trip? 5 miles. So the distance to town, heading out from town A to town B is 5 miles, and it's traveled at a rate of R. In addition to that, we have the time to come back. We're traveling the same 5 miles, but now we're traveling at this new rate, 1.2 times as fast as our rate on the original trip. I hope that helps you to make sense of the problem. Now, to actually simplify the right-hand side, I'm adding or combining these two fractions. That means that I need a common denominator. Well, both of the denominators already have a factor of r, which means when I look at this one and it also has a factor of 1.2, I'm going to multiply by 1.2 on the top and bottom of this first fraction. When I do that, 1.2 times 5 gives me 6 over 1.2r. And I'm going to combine that with the 5 over 1.2r. And so the total time is represented by the expression 11 over 1.2r. If I knew the rate that the train was traveling on the original trip, I could plug that in here, and I would know the entire time that it took to make the trip and its return. Okay, I hope this will help you out, folks. We will practice some of these exercises in class. Please pay attention to our schedule in Google Classroom this week so that you know what you have to preview ahead of time. And I'll talk to you folks soon. Make it a great day.